Hello everyone, this is Cambridge O-Level Chemistry, Paper 4, Alternate to Practical. The subject code is 5070. This is May-June 2023 exam, and this is version 2 of this paper. And we are given 1 hour to solve this paper. So let's start. Question number 1. It says, a student investigates the rusting of iron. Figure 1 shows the apparatus the student uses. So here we see three different test tubes. It's are labeled experiment A, B, and C. In experiment A, we have water and a nail. The second experiment, we have a nail that is enclosed in a test tube with the help of a stopper. And then we have another test tube, or the experiment C, where we have a nail inside water and there is a layer of oil over it. So first part, it says, um, name the apparatus X. The apparatus X is a test tube, okay? And it says state why the stopper is used in experiment B. Okay, so before we start solving this question, so let's see what exactly is required for the rusting of iron. So we are talking about rusting of iron there, and there are two things that are required. Number one, moisture, and that is the presence of water, okay, or H2O. The second thing is oxygen. So in the presence of oxygen and moisture or water, we have rusting of iron that takes place. So in the first case, we have both oxygen and water present. In the second case, we have trapped oxygen, but the stopper won't allow any moisture or H2O to come in. Similarly, in this case, we have the water with us, but it will not allow any oxygen to seep into. Okay, so it says why the stopper is used in experiment B. So in here, the reason of stopper is to avoid moisture or water to go into the test tube. So to avoid moisture slash water to go into the test tube. Okay, so this is the reason for this. So the second case, sorry, part C, it says state why the water in experiment C is boiled before use. So remember, this is boiled water. So, so when we boil the water, if there is any oxygen present in the water, it you can say evaporates, or it goes out of this water, and if the water completely remains or as H2O, or you can say that any trapped oxygen between the water molecules escapes because of the heating of or boiling of the water. So why? So basically, it or removes trapped oxygen from the water. Okay. Then part D, it says state why a layer of oil is used in the experiment. So here, so the layer of oil does not allow oxygen to seep through. So the oil layer does not allow the air, oxygen to go into the water present in the test tube. Okay. Then it says part E, it says the experiments are left for 1 week. Predict in which of these experiments the nail will have rusted. So remember, we have both of these entities available in experiment A. We do not have water here, we do not have oxygen here, or a very, very low amount of moisture and oxygen. So the good case for rusting will be experiment A. So experiment, uh, the nail in experiment A will have rusted. So explain your prediction. Uh, so the just simple reason. So the oxygen and moisture bracket में H2O are present in A, whereas A in excess, whereas so present in A, whereas uh, B does not have oxygen, B does not have water, and C does not have oxygen. So I mean, you're gonna moisture and oxygen are present in A, whereas is lacking in B, and O2 is lacking in C. Sec this is one part. The second part is O2 and H2O are required for rusting of iron. So the last statement, it's good to have this last statement as the first statement, and then you can write oxygen and moisture are only present in it. So a good way to write is that oxygen and water or moisture are required for rusting of iron. In experiment A, both oxygen and the moisture or water are present in excess, whereas where water is lacking in B and oxygen is lacking in C. So this is our first part question. So moving ahead, question number 2, it says aqueous ammonia is a solution of ammonia gas. Okay, a student titrates two samples of aqueous ammonia A and B with 0.5 mole per decimeter cube hydrochloric acid. Okay, so remember aqueous ammonia is NH4H, and this is our HCl, and ammonia gas is, remember, NH3. This is aqueous ammonia. Okay, the student does 4 titrations, 2 with A, 2 with B. Okay, the student follows the following steps: 1 to 8. The first step, it rinses and fills the burette with 0.5 mole per decimeter cube HCl. Step 2, uses a volumetric pipette, add 25 centimeter cube of A into a conical flask. Part 3, adds 5 drops of methyl orange indicator to the conical flask. Step 4, places conical flask on a white tile. Okay. Then step 5, it says add 0.5 mole per decimeter cube hydrochloric acid from the burette while swirling the contents of the flask, adding drop by drop near the endpoint until the solution changes color. Question 6, it says empties the conical flask and rinses it with distilled water. Number 7, repeats steps 2 to 6. And step 8, repeats steps 2 to 7 using aqueous ammonia instead of using aqueous ammonia B instead of aqueous ammonia A. So part A, figure 2.1 shows the burette readings for 2 titrations of A. Record the burette readings in the table. Point 1 below, complete the table with volume used in each titration. Final reading of burette titration. Final reading, we have 15.2. Initial burette reading 0.0. Volume used 15.2. So titration 2, final reading 30.2. Remember, this is 30, this is 30.2. So we have to look at this reading, and initial reading again, this is our initial reading, it's 15.2. Volume used is 15.0. Okay, moving ahead, part B, it says uh, figure 2.2 shows the burette reading for one of the titrations with B. So this is titration 4. Record the burette readings for titration 4 in the table. 2.2, complete the table with the volume and with the volume used in each titration. So final reading of the burette is 34.9. Also, this is titration 3. So um, what would be the volume used here? So 34.9, subtract it with by 0.2, so it comes out to be 34.7. Then record these values. So this is 35.5 and this is 0.6. So 35.5 and this is 0.6. So this comes out to be 34.9. Okay. Moving ahead, explain why the student uses a white tile in these titrations. So basically white tile. So what happens is that when you add methyl orange as a universal indicator in the conical flask, it changes the color. Uh, so and when you are dropping a drop from the pipette into the conical flask, just before the you can say the reaction finishes, the color immediately changes into a colorless solution. And that colorless, it is very difficult to determine what exactly or where exactly is the point where this reaction completes. And that white tile basically gives you good reflection to see all these changes. So just simply the answer is to clearly observe uh, clearly observe the color change, or you can call it as endpoint of the reaction. Okay. Then part D says calculate the mean value of 0.5 mole per decimeter cube HCl needed to neutralize 25.0 centimeter cube of A and B. Remember, for with A, we have 15.2 and 15.0. So for A, you have 15.2 and 15.0. So you have to calculate the mean. This becomes 30.2 and you have to divide it by 2. This comes out to be 15.1. So A is 15.1 centimeter cube. For B, remember the values we have made are 34.7 and 34.9. So 34.7 plus 34.9, add them together, it comes out to be 69.6, and you divide it by 2, uh, comes out to be 34.8. So 34.8 will be our answer. Okay, this is how you calculate the mean of the volume. So moving ahead, it says the equation for the reaction between hydrochloric acid and aqueous ammonia is shown. Okay, so the equation is shown to us. They use the mean value of acid. Remember, the mean value of acid in A is 15.1 to neutralize 5 centimeter cube of A in D to calculate the concentration of ammonia. Okay, so what we have here? So we have here is the HCl. The concentration of HCl is 0.5 mole per dm cube, and we have to find the concentration of ammonia. Okay, so what is happening? So we have 1 mole of HCl neutralizes 1 mole of NH3. Okay, so this is very simple. And the volume of so mean value of acid. So we have volume of acid in A. So the mean value of volume of acid is 15.1 centimeter cube. If we have 15.1 centimeter cube, so what would be number of moles of HCl in this volume? So we have concentration mole per 1000 centimeter cube. Remember, 1 decimeter cube is equal to 1000 centimeter cube. Okay, so and multiply it by the volume used. So we get our number of moles that comes out to be 7.55 into 10 to power minus 3 moles. So 1 mole gives 1 mole of ammonia. So 7.55 10 to power minus 3 moles of HCl will neutralize 7.55 into 10 to power minus 3 moles of ammonia. This is way too simple. And then now we have to find the concentration. So concentration of ammonia. Okay. The concentration is in terms of mole per centimeter cube first. So we have 7.55 into 10 to power minus 3 divided by 25. So what is the volume of ammonia that has been neutralized? 25 centimeter cube. So this comes out to be um, 3.02 into 10 to power minus 4 mole or centimeter cube. But we have to give it in terms of decimeter cube. So in terms of decimeter cube, so remember 1 centimeter cube is equal to 1 divided by 1000 decimeter cube. So just instead of centimeter cube, I can simply write 3.02 into 10 to power minus 4 mole. And instead of centimeter cube, I will write 1 by 1000 decimeter cube. And this comes out to be, this 1000 goes up, multiplies with it, it comes out to 3.02 mole per decimeter cube. So this is my concentration of ammonia that is used in this equation, in this reaction. Moving ahead, part F, it says calculate the volume of ammonia gas measured at room temperature and pressure dissolved in 25 centimeter cube of A. So we have to basically um, find the volume, and it says volume of 1 mole of gas at room temperature is 24 decimeter cube. So first of all, let's find out how many moles, number of moles of NH3 dissolved in A are 7.55 into 10 to power minus 3. Okay, so these are the number of moles. So it's very simple now. 1 mole of gas is equal to 24 decimeter cube. So 7.55 into 10 to power minus 3 moles of gas is equal to 24 multiplied by 7.55 to the power minus 3. And this comes out to be approximately or 0.1812. So up to 2 significant figures, we can simply write 0.18 decimeter cube. Okay. Then in part G, it says use your answers in D and F to calculate volume of ammonia gas measured at room temperature and pressure dissolved in 25 centimeter cube of B. Okay, so first of all, now our solution has changed. So volume of acid is different. So volume of HCl used for B, and this comes out to be 34.8 centimeter cube. Remember, concentration of HCl 0.5 mole per dm cube. So number of moles of HCl used are zero point 0.5 divided by 1000. Remember, this is mole, this is centimeter cube, multiply by 34.8 centimeter cube. So the number of moles comes out to be 0.0174 moles. So 1 HCl neutralizes 1 ammonia. So 0.0174 HCl will neutralize 0.0174 moles of ammonia. Moles of ammonia. So these are the number of moles of ammonia that are used. So 1 mole is equal to 24 decimeter cube. 0.0174 moles will be equal to 24 multiplied by 0.0174 decimeter cube. This comes out to be 0.4176 centimeter cube. Again, we have to write an answer close to 2 decimal places. So 6, it will be 0.418 further to 0.412 decimeter cube. 0.42 decimeter cube. So approximately, this is the answer. So moving ahead, it says the student rinses the burette with zero point 0.5 mole per decimeter cube hydrochloric acid immediately before it is filled. Explain why the student should not rinse the burette with distilled water immediately before it is filled with zero point 0.5 mole per decimeter cube of hydrochloric acid. So remember, while rinsing, there will be some water that will stick or remain inside the burette, and once it remains inside the burette, and once you add acid to it, it will change the molarity or concentration of the acid, which eventually change the overall results of the experiment. So just simply write, so some water will remain inside the burette, when HCl is added, the water will dilute it, thereby decreasing the molarity slash concentration of the HCl. This changes the results of the experiment. Okay, so the concentration is very important and it changes. This is how it affects. So suggest why universal indicator is not suitable for these titrations. So the reason is that the universal indicator is unable to give us a precise endpoint for the completion of the reaction. The reason is that once you are just simply putting a drop into the conical flask from the burette, just at a certain instant, and you have to basically shake the flask as well. So it just simply changes the color. And you are just not sure, okay, fine, this is the precise moment. You add a little one drop more and you add a little one drop less. Uh, there is a or so this is a possibility of human error, less precise reading, and even a drop difference in concentration, uh, um, um, or a difference, even a one drop of volume will make a huge difference in the molarity or the concentration we are getting out, and that is why generally it is considered. Um, so simply say the color change is not precise slash specific enough to establish the endpoint slash completion of the reaction. Okay, so this is how you go about this question. Then question number 3, it says a student investigates solution W and solid X. Okay, so we have a solution and a solid X. So solution W is green in color and contains iron 2 ions. Okay, describe how W can be shown to contain iron 2 ions. Remember, simply add aqueous sodium hydroxide to the solution. A green precipitate is formed. The precipitate is insoluble in excess. This is one way. The other way is that you can simply say that add aqueous ammonia. Again, a green precipitate is formed, which is insoluble in excess. Okay, so these are the two. You can write any one of it. Um, you can say add mm, aqueous. Oh, aqueous sodium hydroxide to a sample of W in a test tube. Okay. Green precipitate is formed, which is insoluble in excess NaOH. Okay, so this is a good answer. You can also use aqueous ammonia to for this test as well. Again, at the end of your answer booklet, these tests are given, so you can just simply see from there and just write the answer. Then it says excess W uh, is added to acidified aqueous potassium manganate. Remember, acidified is an oxidizing agent. Oxidizing agent. Okay, so this is an oxidizing agent. So describe the color change seen. So remember, potassium permanganate is purple in color, and once it is completely oxidized, the iron changes to iron 3, iron 2 changes to iron 3. So the oxidation is complete. The final color, you can say the potassium manganate. So excess W is added to acidified potassium. So this whole thing is an excess. So W is in excess, and it contains W is green in color. So remember, this is green in color, and iron 3 is generally reddish brown in color. And reddish brown and purplish color turns out to be something nearish yellowish sort of color. So the answer, so the color change from purple, initially potassium permanganate, you add excess to it, it turns to yellowish, yellow, you can see yellow. Okay. Do not write colorless here because the excess is W. If potassium permanganate would have been in excess, then it would have changed from purple to colorless, which indicates that all the oxidizing agent has been used. But in case W is in excess, so the color will be the dominant color that is seen will be the color of the final solution, and that is determined by the excess solution or the color of the solution that is in excess, and that is in W. So remember, so moving ahead, part 3, it says describe the observation made when few drops of aqueous ammonia and then excess aqueous ammonia are added to the mixture in 2. So you are adding aqueous ammonia. So since W is in excess and it has oxidized, so now you are actually doing a test for Fe3 positive ion. This has changed Fe2, Fe3, and now you are testing for Fe3 positive ion. So with the Fe3 positive ion, with a few drops, you'll get a reddish brown precipitate is formed. In excess, the precipitate again is insoluble. The precipitate is insoluble in excess. Okay. So now moving ahead, part B, it says solid X is the shiny gray metal. Remember, this is a metal. So um, the test the student does on X are shown. Okay. In table 3.1, some of the observations for these tests are also shown. Okay. So it says add dilute acid to X in a test tube. A gas is produced. The gas produced is tested. It says the solid disappears, solution remains colorless and becomes warmer. So remember, if a metal plus acid, so there will be some salt plus gas, and gas is generally H2, hydrogen gas. Okay, so then it says part 2, dilute nitric acid. So HNO3 and add aqueous silver nitrate, AgNO3. Okay, to some of the solution from test 1. So now you have this solution. This this solution, if this is the test tube, so you have this solution. There is some salt and gas that comes out. So sample of this. So this salt is now what we are testing. So it has metal X plus the um, uh, the negative ion from the acid. So you can call it as whatever the ion would be. So dilute nitric acid and aqueous silver nitrate. Okay. So just ask yourself what exactly they're testing for. So this test, if you go and check your end of uh, you can say answer booklet, you'll find out that this test is generally used to check for chloride ions, bromide ions, or iodide ions. The solution remains colorless, so we don't see any precipitation. It means that these ions are not present. Okay. Then you add dilute nitric acid and aqueous barium nitrate. So you add barium nitrate, soluble nitrate, and dilute HNO3. Remember, this is a test for sulfate ions. Again, you can go at the end of your answer booklet and see the test for sulfate ions. It is acidified with dilute nitric acid and then aqueous barium nitrate. So what happens? A white precipitate is formed. So congratulations, you have found out the negative part of your salt. So your salt is a sulfate salt. So whatever the metal X will be, so X2SO4 will be your salt. Uh, Whatever the X one positive, two positive, three positive, or whatever. So apparently it looks something like this. So it would be a sulfate salt. So let's see. It says predict the identity of the gas. So metal plus an acid, it will give you a hydrogen gas. As is the hydrogen gas. So test for a hydrogen gas. We can say collect the gas in a test tube and take a glowing splint near it. Okay. What will heard? A popping sound. A popping sound is heard. Okay. So this is the test for hydrogen gas. Remember, X is the metal plus acid. You don't know what acid it is. It is a sulfate ion. So basically, you can easily say that this acid is H2SO4. So what will happen? So X2SO4 will be formed plus H2 gas is released. Just balance this equation yourself. So it would be something like this. Okay. Then it says the observation of test one are incomplete. State one other observation that the student makes for test one. So basically, when hydrogen gas is coming out, there would be some bubbles. So effervescence or bubbling of hydrogen gas is seen. You can simply say bubbles or slash since. Oh, effervescence. Okay, that's fine. Oh, is seen. Okay. Then part three state the conclusion you can make from test two. So remember while testing. So this is the test two. So we can clearly say that the uh, solution does not contain Cl, Br, or I negative ions, or they are actually halides. Um, the solution does not contain chloride, bromide, and iodide ions. And basically, these are also called halides. Okay. State the conclusion you can make from test three. So from the test three, you can say that the solid, you can say it's a test for sulfate ion or the anion. You can say the solution contains sulfate ions, SO4 to negative. Okay. Solution contains sulfate ions. Okay. Then it says identify the acid used in. So identify. So we all know it is the sulfate is coming from sulfuric acid, uric acid, or you can write to H2SO. So suggest an identity of metal X. So remember, it's a gray metal. Zinc, magnesium, both are uh, grayish metals. So since you can say you can all both write magnesium or zinc, and they all both for their sulfates are the white precipitates. So what I will go for, I will go with the zinc because the magnesium or the information of magnesium is not given at the end of the answer booklet. So at the end of the answer booklet, your answer booklet gives information about aluminum, iron, copper, chromium, calcium, ammonium, iron, and zinc. There is no mention of magnesium. So a good possibility for the student is to go for zinc. Okay. The last question for this paper. Hmm. So it says the baking soda is used to make bread rise. When baking soda is heated, it decomposes and carbon dioxide gas is released. The baking soda also decomposes gradually when it is stored. The longer the baking soda is stored, the less carbon dioxide is released, or less carbon dioxide is released, less carbon dioxide it releases when it is heated. Plan an investigation to show plan it to show which of the two different samples of baking soda has been stored for longer. The plan should include the use of common laboratory apparatus and two samples of baking soda. No chemicals should be used. So your plan should include the apparatus needed, the method to use, the measurements to take, variables to control, and how to use the results to determine which sample has been stored for longer. You may draw a diagram to help your to answer your question. So remember, let's draw. So we'll basically have a measuring digital measuring tool. So we can measure. This is our NaHCO2. So this is your baking soda. So this is uh, grams weight. You can measure the weight of sample A and sample B. And what you need is you need a Bunsen burner, a stand, a conical flask, and attached to a syringe pump. Okay, so attached to a syringe. So you can live in this is your syringe. This is your conical flask. This is your Bunsen burner. Okay. So what you will be doing is that you will be first of all taking two conical flasks. So you need two conical flasks. You need two conical flasks and measure them empty, and then put equal weight of uh, baking soda or sodium bicarbonate into it and measure it again. Record the reading again. So once you have recorded it, then attach the syringe pump and put it over the Bunsen burner and heat it for say 5 minutes. So after 5 minutes, record the reading or on the syringe and also measure the mass of the conical flask. Then repeat the same thing with the second conical flask. Heat it for 5 minutes, measure the reading on the syringe, and measure the weight of the conical flask. So from this, you can say that which of the experiments gives you the more volume or bigger reading on the syringe. It means that that is the sample of sodium bicarbonate or baking soda that is not that has been stored for lesser time. Similarly, the weight of the flask or the if you're going to talk about weight, so the flask having lesser weight uh, or yes, or the flask having lesser weight will be the one which is having baking soda stored for less amount of time. Okay, so moving ahead, you can always draw the diagrams yourself. So let's try to write down what we have just discussed. So first of all, you will say uh, take two conical flasks and measure the weight oh, using a digital balance. Now, measure two equal take two conical flasks, measure and record. That is also important. Record the weight. So measure two equal samples of baking soda and add each of them to the individual flasks. Again, record, measure and record and record the weight of the flasks. Okay. Now, uh, then, okay, that's fine. Now attach a syringe pump to the flask and heat it over a Bunsen burner, say for 3 minutes. Okay. Then again, measure and record volume of gas produced using the syringe and also the weight of the flask. Okay, then says repeat the process with the other flask. Now analyze the readings. The test giving more volume of gas slash reading on the syringe is the sample stored for less amount of time. Similarly, the weight, the test with the weight loss in more weight loss is the sample stored for less amount of time. Okay, so that is how you write or go with this uh, question and route the solution for it. Okay, so I hope you would have learned from this effort, and I wish you best of luck for preparing for this course and your exams and your learning and for your future. So take care and see you in the next video. Bye bye.